a potassium permanganate solution, you have to standardize the potassium permanganate. So potassium permanganate is called secondary standard. So dichromate is primary standard, potassium permanganate is secondary standard. So the advantage is potassium dichromate is primary standard. But the disadvantage of potassium dichromate is that the color of potassium dichromate is not so intense, and as a result of this, to know the end point in a potassium dichromate titration, dichromatic titration, you have to use certain indicators, redox indicators. Just as in case of acid-base titration, you have acid-base indicator. Similarly, in case of dichromatic titration, you have to use certain redox indicators, which will actually give you the end point, will enable you to detect the end point. On the other hand, here the potassium permanganate has got the advantage because permanganate itself has got such a strong color that you need not have any external indicator. Potassium permanganate's color, whenever the reaction is complete, excess 1 drop of permanganate, excess 1 drop of permanganate is sufficient. Excess 1 drop of permanganate is sufficient to impart the color in the solution. So for potassium permanganometric titration, we don't need any external indicator. So dichromate and permanganate has got equal advantage and disadvantage, and depending on the need, we may use dichromate and permanganate. But here in these experiments, in our experiments, we shall use potassium dichromate. Now, since you are using potassium dichromate, the oxidizing agent, standard oxidizing agent, so obviously you cannot react it with ferric. So ferric has to be reduced to ferrous ion. Excess reducing agent must be decomposed, and then the ferrous ions so generated may be reacted with potassium dichromate, may be titrated with potassium dichromate. And as a result of this, then you can do the titration and find out the endpoint. So our principle will be for sublight ferric solution estimation. Our principle will be, we shall take the ferric solution in a conical flask, and then we shall reduce ferric iron using a reducing agent. Excess reducing agent will be decomposed because otherwise it will react with the dichromate, the oxidizing agent. And then the generated ferrous ion will be oxidized, will be titrated using the standard potassium dichromate solution, and we can detect the endpoint using a suitable indicator. That is our theory. Now, for your viva-voce, you must know some things. First of all, regarding what are standard solution, what is primary standard, what is secondary standards, these things you must know. So primary standards are those standards whose solution can be prepared by weighing, and as a result, primary standards must be available in 100% pure quantity, in very high purity, and you must be able to weigh the solution in presence of air and moisture. That means it should not absorb moisture from the surrounding, it should not be oxidized by the real oxygen, right? It should not react with the real oxygen, and its solution must be sufficiently stable. On the other hand, secondary standards are those standards which does not satisfy or do not satisfy those criteria. As a result of this, for secondary standard solutions, you have to first of all standardize those solutions using a primary standard. So for instance, potassium dichromate is a primary standard. On the other hand, if you have potassium permanganate solution, then you have to first of all prepare an oxalic acid solution, whose standard solution you can prepare, and then using that oxalic acid solution, you have to standardize the permanganate solution. Similarly, sodium hydroxide, HCl, H2SO4, all of them are secondary standard because you cannot either get the solid compound as such, or it may be hygroscopic, etc., etc. So for this sodium hydroxide, HCl, H2SO4, etc., all of them are secondary standard. So if you want to prepare a standard solution of sodium hydroxide or HCl or H2SO4, what you have to do again? You have to prepare a standard oxalic acid solution. Oxalic acid is a standard solution both for redox titrations like potassium permanganate standardization as well as acid-base titration. Oxalic acid is both an acid as well as reducing agent. So you can prepare an oxalic acid solution, standard solution, and you can use it to standardize an oxidizing agent like permanganate. You can also use it to standardize a base like sodium hydroxide. So suppose I ask you to prepare a standard HCl solution. So first of all, you will prepare a standard oxalic acid solution, primary standard. Then using that oxalic acid solution, you first of all prepare a standard sodium hydroxide solution by titration. And using that sodium hydroxide solution, you prepare the standard HCl solution or sulfuric acid solution. So this must be very clear what is primary standard and what is secondary standard. Now, what is our method? What is our method of estimation? The first part, that is the iron estimation. So we take the supplied iron solution using a pipette. Usually we take a 25 milliliter pipette. In pipette, you know, there is no graduation. There is only one mark which corresponds to that given volume. So if you have a 25 milliliter pipette, there will be one mark on the pipette which corresponds to 25 milliliter. Unlike bullet, where you have the graduation throughout the barrel, but in pipette there is only one mark indicating total volume. So if you have a 10 milliliter pipette, then there will be one mark up to that point, it is 10 milliliter. If you have a 25 milliliter pipette, then you will have one mark on the pipette. At that point, you have the 25 milliliter, etc. So using a 25 milliliter pipette, we pipette out the given supplied ferric solution in a conical flask. And to this conical flask, then we add 6 milliliter of concentrated HCl, because the reducing agent reduction will be carried out in strongly acidic medium. So we add, and moreover, for dichromate or permanganate titration, we require strong acidic condition, because for dichromate or permanganate to act as an oxidizing agent, they require strong acid so that these oxide ions can be easily converted to water. Okay, so we add 6 milliliter of concentrated HCl solution to a conical flask which already contains 25 milliliter of pipetted out ferric solution. Then what we do? To that, this solution is then warmed on a hot plate. This solution is then warmed on a hot plate. Remember, I am saying that solution is warmed on a hot plate. It is not boiled, because ferric chloride is sufficiently covalent compound, and if you boil a ferric chloride solution, ferric chloride is steam volatile and some amount of ferric chloride will go away with steam. So when you heat the solution, you must take care that the ferric chloride solution where the ferric ion is dissolved in HCl medium, it does not boil. There should not be boiling. You have to warm it to 50 to 60 degrees centigrade, and once the solution is sufficiently warm, to this you add small pieces of aluminium foil. Small pieces of aluminium foil is added to the solution while continuing heating. What will happen? This ferric iron will react with aluminium. Ferric will be converted to ferrous, and aluminium will be oxidized to aluminium 3+. So 1 mole of aluminium will reduce 3 mole of ferric, because aluminium gives 3 electron and ferric takes 1 electron to be converted to ferrous. Now ferric solution was strongly yellow in color in presence of HCl because of a chloride to ferric charge transfer band, and whereas aluminium chloride is colorless, and ferrous solution, ferrous chloride or aquoferrous ion, is very light green, and as such it appears as colorless. And as a result of this, when you add aluminium foil and heat the solution, ferric is converted to ferrous, and this is actually evidenced by the fact that the deep yellow solution gradually fades out and when all the ferric iron is reduced, the solution appears almost colorless, very light green or almost colorless. So you can understand easily when your reduction is complete. It will be shown by the fact that the yellow colored, strong yellow color of your solution has completely vanished, and the solution has turned almost colorless or very light green. At that point, you destroy any remaining aluminum foil that may be added, because you may have added excess aluminum foil. Try to avoid adding excess aluminum foil, but if you have already added excess, you have to destroy all the aluminum foils by heating in HCl medium. So when all ferric is reduced to ferrous and excess aluminum has been converted to aluminum chloride, all aluminum has been destroyed. At this point, you are ready for the next step. So what you do, you stop heating the solution, and first of all allow it to come to room temperature, and then you when it comes to room temperature, you further cool the solution, the conical, under a tap water, running tap, right? Ensuring that tap water should not go inside your conical flask. So you cool the solution under tap water, but you must ensure tap water should not go inside your conical flask. So once the solution is cooled, then to this solution you will be adding 100 milliliter of water so that acidity is properly adjusted. About say 2 to 3 milliliter of phosphoric acid, orthophosphoric acid, and a few drops of, say 2 to 3 drops of an indicator, an acid-base indicator, which is called barium diphenylamine sulfonate. Barium diphenylamine sulfonate. So barium diphenylamine sulfonate, the structure is like this. So you can see there are 2 phenyl rings connected by an amine group in each, and there are 2 sulfonate groups attached to the para position of the amine group. So this is the reduced form of the indicator, and it is colorless. And to balance the sulfonate charge, you have the barium ion. So barium diphenylamine, you have the 2 phenyl groups. That's why it is diphenylamine sulfonate. And this barium diphenylamine sulfonate is colorless. And this is the redox indicator. When your titration will be complete, the excess oxidizing agent that will be added after your titration, ferrous ion is completely titrated, the excess oxidizing agent will convert this reduced form of the enzyme to its very complicated oxidized form, which is shown here, very complicated oxidized form, and the color of the oxidized form is blue violet or red violet, and that color change will indicate that the end point is complete. So you can easily understand the end point by looking at the color change. So what you do, I repeat, after ferric has been reduced to ferrous and you cool the solution, then you add 100 milliliter of water to the solution. You add a few milliliters, around 2 to 3 milliliter of phosphoric acid, and then you add few drops of the barium diphenylamine sulfonate indicator. The solution is still colorless. Now you titrate the solution with potassium dichromate from the burette gradually. At the end point, when you titrate with potassium dichromate, ferrous iron will react with dichromate and will be converted to ferric. And dichromate, all of you know, dichromate reacts with dichromate takes the electron given out by the ferrous iron. These are electrons, 6 electrons plus hydrogen ion. It is converted to chromium ion. And you can calculate what is the equivalent weight of dichromate, that you can calculate. And we have to prepare 250 milliliter of N by 20 dichromate solution, which I have calculated here. That means you have to take around 0.613 gram of the potassium dichromate in a 250 milliliter volumetric flask, and then you fill up the volume and you will get a standard N by 20 dichromate solution. So in order to titrate the ferric iron, we need to prepare a standard solution of N by 20 dichromate solution in 250 milliliter. To do that, we calculate what is the amount of potassium dichromate required. Since potassium dichromate is taking 6 electrons in this reaction, so equivalent weight of potassium dichromate is molecular weight divided by 6. And so for 250 milliliter, 1 normal, we require M by 24, and for this we can calculate easily. For 250 milliliter N by 20, it is 0.613 gram of potassium dichromate that is required. So before you start the iron titration, you have to prepare a standard dichromate solution using this method, right? So you have to weigh out around 0.613 gram of dichromate in a conical flask, in a volumetric flask, and make up the volume up to 250 milliliter. So using that standard dichromate solution, you titrate your solution, your ferrous solution, where these ingredients has been added. And when the titration is complete, so initially as you go on adding dichromate, ferrous will be oxidized to ferric, and when all ferrous ion is consumed, then this BDS will react with the excess 1 or 2 drop of the oxidizing agent, and it will be converted to the oxidized form, which has got a blue-violet color. And this blue-violet color will give you the end point. So you note down the reading and do 3 successive titrations, at least 3 successive titrations, and take an average of the reading. Now, just a point or two about the redox indicator. So you know acid-base indicators, acid-base indicators are weak acid or weak bases, and in the so HIN equal to H plus IN minus. So it can, in case of acid-base indicator, the indicator can exist in protonated form or non-protonated form, and this protonated form has got one color. This non-protonated form or deprotonated form has got another color. So when you go from acidic region to a basic region, there is a certain change from HIN to IN minus, and it shows a color change. Similarly, for redox indicators, again, they are weak oxidizing agent or weak reducing agent. And like the acid-base indicator, here the redox indicators can exist in 2 forms, the reduced form and the oxidized form. And depending on the redox potential of the solution, it may change to IN red or IN ox. These 2 forms has got 2 different colors. So for instance, in this case, initially the indicator was in the reduced form, and then when the titration is complete, when you add excess oxidizing agent, then using that oxidizing agent, IN red indicator reduced form is converted to indicator oxidized form, and it shows a strong color change. So this is the theory of the redox indicator. Now, again, 1 or 2 questions must be answered, that what is the role of phosphoric acid? Why we are adding phosphoric acid before the titration? The role of phosphoric acid is twofold, right? Role of phosphoric acid is twofold. First role is that during the titration, you are oxidizing ferrous ion to ferric ion. Now, ferric solution, as I'll be demonstrating, ferric solution has in presence of chloride, because you are doing the titration in presence of HCl. So ferric solution has got a strong yellow color because of chloride to iron charge transfer, ligand to metal charge transfer, and because of this strong charge transfer, ferric solution has got a yellow color. Now, if this ferric solution if this ferric iron is kept bare, that means if it is not taken care of, then this strong yellow color of ferric ion will interfere with the color change of the indicator. You may not be able to judge, or you may not be able to see the sharp color change of the indicator. So the color of the ferric iron that is generated during the titration will interfere with the detection of the color change at the end point due to the transformation of the indicator from the reduced form to oxidized form. So in order to avoid that, in order to avoid interference of ferric iron in the color change, what we are doing, we are adding phosphoric acid. This phosphoric acid will react with ferric iron, and will convert into a phosphate complex. So there in the complex we have 5 aqua ion and one hydrogen phosphate ion. Now here this ion in presence of phosphate, ferric iron is colorless. So the phosphato complex makes the solution colorless, and as a result of this, indicator endpoint detection is easier. So first point is that why we add phosphoric acid. The one function of phosphoric acid is to complex the ferric iron that is generated during the titration, and this ferric iron, which otherwise would have given you a strong yellow color and interfered with the detection of the endpoint of the titration, it is complexed by the phosphoric acid, and this resultant phosphate complex is colorless, and as a result of this, now the interference is removed and you can detect the endpoint easily. So this is first importance of the phosphoric acid. The second importance is that all of you are again probably aware with this equation, which is called Nonstick equation. So ferric ferrous potential equal to E0 ferric plus ferric ferrous plus 0.059 by N log ferric iron by ferrous iron. Now, all of you again from your knowledge of higher secondary or the school living examination, you know what is indicator range. In case of acid-base titration, you know for each kind of acid-base titration, strong acid, strong base, weak acid, strong base, weak base, strong acid, etc. For each kind of titration, you need different indicators because the pH change has to be matched with the pH range of the indicator. So just as in case of acid-base indicator, each indicator has got its own indicator range where it changes color from one form to other form in that pH range. Similarly, in case of acid-base titration also, each acid-base, in case of redox titrations also, each redox indicator has got its own indicator range. That means it will change color in a certain redox potential region, and you have to choose appropriately the indicator. Now the problem is that during our titration we have chosen a BDS indicator because it is less costly. We could have used a much more beautiful indicator whose indicator range exactly matches with the ferric ferrous titration, ferric ferrous endpoint, but that indicator is very costly. So to reduce cost, we have used BDS indicator, but the disadvantage of BDS indicator is that if we do not take care of this ferric iron by complexing it, then the redox potential near the end point of ferric ferrous titration is such that much before the end point, the BDS indicator will show you the color change. So I have written here that the BDS indicator, the indicator range is such that it will show color change when 75 to 80% titration is complete. That means still 20% titration is yet to be done. At that region, BDS indicator will show color change because for BDS indicator, the indicator range is lower, whereas for our titration, the equivalent point redox potential is much higher. As a result of this, before the higher redox potential is reached, the BDS indicator will change the color when almost 75 to 80% titration is done. So what we are doing here from this Nernst equation, as you can see, that if you can remove ferric iron from this numerator of this log, so if ferric iron can be removed by complexation, then this factor will decrease and the overall redox potential of the system will decrease. So we want to decrease the redox potential at the equivalent point, and we want to bring it to the point where it matches with the indicator range of the BDS indicator. So I repeat, what is our second objective? We are adding phosphoric acid. We are adding phosphoric acid with the assumption that phosphoric acid will form complex with the ferric iron. This will first of all make it colorless, so its interference during endpoint detection is actually diminished. And second point is that by removing ferric ion in the form of complexation, we are decreasing the free ferric ion concentration. As a result of this, overall redox potential is decreased during the endpoint, and so now the endpoint will occur at a redox potential where it matches with the indicator range of the BDS indicator. So role of phosphoric acid is twofold. One is to complex the ferric, or in both cases you have to complex the ferric iron, and by complexation of ferric iron we achieve two results. One is its color is suppressed. The strong yellow color is converted to a colorless form, so that your indicator endpoint detection is easier. And second thing is that it is decreasing the free ferric iron concentration, thereby decreasing the redox potential of the endpoint. And now the redox potential in presence of phosphoric acid at the endpoint will match the indicator range of the BDS indicator. And so BDS indicator will now show correctly the endpoint. So these are the two roles of the phosphoric acid. And this is the reaction: potassium dichromate. It takes 6 electrons and 6 ferrous iron gives 6 electrons. So potassium dichromate reacts with 6 ferrous iron and 14 H plus. The dichromate is converted to chromium ion, 2 chromium 3 plus. Ferrous iron is converted to ferric, and you get the potassium ion and 7 water molecules, right? And you can calculate. So if you know what is the volume of using V1S1 equal to V2S2, first of all, what is V1? V1 is the volume of the dichromate you have consumed, right? V2 is the S2. This S1 is the concentration of the dichromate. So volume of the dichromate multiplied by the concentration of the dichromate. V2 is the volume of the ferric solution. You have taken 25 liters, that you know. And S2 is the concentration of the ferric solution, which is unknown to you. So using V1 S1 equal to V2 S2, since V1 is known, S1 is known, V2 is known, so you can easily find out the S2, and from that you can calculate what is the strength of the ferric solution, and then convert the ferric iron concentration into the grams per liter by multiplying it with the equivalent weight of ferric iron. So since ferric takes 1 electron to be converted to ferrous, so here equivalent weight of iron is same as that of the molecular weight, which is 55.8. So whatever the strength you are getting here in terms of normality, if you multiply it by 55.8, you will get it in grams per liter. Okay, the strength of the ferric ion in grams per liter, that can be easily seen. And I have given you the video. I shall play the video again here, so you can easily see the titration. Pardon? So you can see here, it is a ferric chloride solution which is being pipeted out and is taken in a conical flask.
Now we take hydrochloric acid in solution 20 ml and add this HCl 20 ml into the FeCl3 solution.
20 ml was not required, 10 ml is sufficient. So we are adding aluminium foil to the solution.
The hot plate. We heat the solution into the hot plate. When you heat the solution, the aluminium foil start to dissolve and the reduction will be continued. And solution from yellow transfer to colorless. the aluminum foil will dissolve into the solution. Look at that. Look at that. The aluminum foil is completely dissolved and yellow color of solution transferred to colorless. So finally we get the colorless solution. Then the hot colorless solution we cool down under tap water. Phosphoric acid 6 ml, and then the phosphoric acid transfer into the cooled solution. Then we take the BDS indicator, that is barium diphenyl amine sulfonate, and add 2 or 3 drops of indicator into the solution. Now we start the titration with potassium dichromate, which is taken in urate. Dropwise add potassium dichromate to the iron solution, and look at that, the color change will start. Color change. That color is spread violet color, which is endpoint color. So endpoint is very near. Look, this is carefully. In that point, we have to titrate very carefully. So endpoint is very close now. This is the violet color. We stop the titration and we get the which is violet color. So we get the endpoint color, which is violet coloration, and now we take the endpoint of the burette reading, which is 23.6 nearly. So now repeat this process thrice and get the burette reading every time. We get the burette reading which we get initially plus minus 0.1. That means 23 point.
Okay, so let us forget about that. So now what about the data? Some of the students wrote to me, sir, there is no assignment in the practical. Obviously, the assignment will be given after you get the experiment, right? So you see, this is I have supplied you this PDF file. Here the process is given. Okay. Now come to the data. First of all, preparation of standard dichromate solution. So weight of potassium dichromate taken into 50 milliliter. Write down for here you will write weight taken is 0.615 gram. Weight taken is 0.615 gram. So please write down here. You will write amount of dichromate taken is 0.615. Okay. All of you please note down here. The amount of dichromate taken is 0.615. So strength of the dichromate solution is weight of the dichromate taken divided by weight of the dichromate required multiplied by the desired strength. So weight of dichromate taken, and I have explained you that for preparation of N by 20 dichromate, I have told you we require around 0.613 gram. So weight required is 0.613, weight taken is 0.615 multiplied by N by 20 will give you the strength of the dichromate solution in terms of the N by 20 region. Now initial burette reading, we assume initial burette reading is always 0 because burette reading starts from the top, it is 0, and it at the bottom it is 50. So when you fill up the burette, initial reading is always 0. So in all cases you can write down initial burette reading is 0. The final burette reading, that again you note down, there are 3 readings. First reading is 22.0, First reading is 22.0, second reading is 22.1, and third reading is 22.0. So 22.0, 22.1 and 22.0. So volume of dichromate that has been taken, it is equal to again, because initial volume is 0, so this will be 22.0, 22.1 and 22.0. Okay. Now there should have been another column here, so you can add another column here, and here you write the average volume of your mean volume of the dichromate. So you make extra column here and you write down this extra column. Here you write down the average volume of the dichromate. Okay. So
Sir, you will send this PDF to us, right?
Yes.
Sir, will you send this PDF to us?
I have already uploaded it in the classroom.
Oh, yes, sir. Thank you.
So here you make the correction that there should be additional column where you have to find out the average volume. Okay. Now, generally when you have two concurrent readings, just as here we have 22.0, 22.1 and 22.0. So there we can neglect the non-recurrent reading, and we can take 22.0 as the standard value or 22.0 as the volume value. So if you have reading as 22.0, 22.0 and 22.1, it will be 22.0, because if you average out, it will be 22.03. So it can be taken as 22.0. So from that you calculate the strength of the ferric solution using V1S1 equal to V2S2, and then the amount of ferric iron supplied solution in grams per liter will be, as I have told you, it is the class. It is equal to the strength of the ferric solution that you have find out in terms of normality multiplied by 55.8. So this is a very simple result and very simple experiment. You can easily do it. Okay. Our next experiment is more complicated. In fact, this is should be say experiment number 1, and experiment number 2 is this one, which is estimation of copper ion in a supplier solution. Usually it is a brush, but we supplied it in the estimation of copper ion. Now this experiment is divided into two parts. One is it is standardization of the sodium thiosulfate solution, and then using that standard thiosulfate solution, you have to estimate. You have to first of all titrate the copper solution. So let us try to find out first of all what is the theory behind this. Okay. Theory behind is that forget about this experiment is what is called iodometric titration. Now in iodometric titration, what we do, we take a standard oxidizing agent, or we take an oxidizing agent, react it with excess potassium iodide, so that the oxidizing agent reacts with the iodide, and it is converted, iodide is converted to iodine. The liberated iodine is titrated with sodium thiosulfate using starch as an indicator. And you know, starch with iodine, it gives a blue color, right? And at the end point, when all the iodine has vanished, that blue color will vanish and you will get a colorless solution. And so you can easily measure what is the amount of iodine that is produced, and from that you can calculate what was the amount of oxidizing agent that was there. So this is called iodometric titration, whereby the liberated iodine, by the action of an unknown concentration of oxidizing agent, is titrated with sodium thiosulfate solution, and from the volume of sodium thiosulfate consumed and from the strength of the sodium thiosulfate used, we can find out what is the amount or what is the equivalent weight of sodium thiosulfate, that is what is the equivalent amount of sodium thiosulfate that has been consumed, and from that we can back calculate using V1S1 is V2S2 what was the concentration of the oxidizing agent. Now the reaction is given here: iodine in presence of thiosulfate, iodine takes 2 electron and is converted to 2 iodide. So each iodine molecule takes 2 electron and is converted to 2 iodide, and 2 thiosulfate ion, right? 2 thiosulfate ion each gives out 1 electron, and then these 2 thiosulfate ions are converted to S4O6 2 minus, which is called tetrathionate ion. So iodine plus 2 thiosulfate is converted to 2 iodide plus S4O6 2 minus. So this is thiosulfate and this is tetrathionate ion. Okay, and we monitor this reaction using starch as an indicator. Now here, for iodometric titration, you must take several precautions. First precaution is that iodine is very volatile, and so you must take care that these titrations are carried out very rapidly, and usually these titrations are carried out in long-mouthed conical, so that as when they are long-mouthed conical, so that the iodine volatility decreases. In a beaker, because of its very open mouth, it can easily go out. But if you take a long-necked conical, long neck conical, then iodine will go out slowly, and you must do it very fast, these titrations. Second thing is that there should not be any source of heating during titration. That means any hot plate or burner should be avoided on your table where you are doing the titration. The other thing, and in order to manage the volatility of iodine, what do you do? Usually these titrations are carried out in presence of excess potassium iodide. Iodine, all of you know again from your school knowledge that iodine reacts with potassium iodide to make it soluble Ki3, and compared to iodine, I3 minus is much less volatile because of its high solubility. So if you add excess Ki, almost all iodine will be converted to Ki3 and volatility will decrease. But obviously you cannot add very large excess of iodide, because again iodine or iodide is very costly. So you have to compromise that you will add excess Ki, and you will also ensure that titrations are done very rapidly and there is no heating source, etc. The other point is that potassium iodide, what you are doing, usually you are adding potassium iodide to manage this iodine, right? But unfortunately, potassium iodide is actually easily oxidized by air, particularly in presence of sunlight. So if you again carry out the reaction with lot of time, spending lot of time, there is chance that particularly in presence of sunlight, the iodide may be oxidized to iodine. So your experimental result may be erroneous. So again, you must do the experiment rapidly, and you must avoid direct sunlight during in the area where you are doing the titrations. And very often we want to keep it in dark. When potassium iodide is used, sometimes we prefer a dark condition for the titration, as we shall see. The other problem is that I have already discussed the sodium thiosulfate again is not a primary standard, because sodium thiosulfate is obtained in crystal as sodium thiosulfate 5H2O. Now this sodium thiosulfate 5H2O is actually is a efflorescent compound. You have probably learned again efflorescent and deliquescent compound. So efflorescent compounds are those compounds which actually gives out its water crystallization. So sodium thiosulfate crystals try to leave some of the water molecules, and so you cannot weigh exactly the amount of sodium thiosulfate, because your sodium thiosulfate crystal may not contain all 5H2O. There may be some molecules which contains less water. So by weighing, it is not possible to accurately get the strength. And moreover, sodium thiosulfate solution again is not very stable. It undergoes bacterial decomposition, and in presence of air, particularly in urban environment where there is lot of carbon dioxide and pH of the air is maybe slightly lower, then in presence of this carbon dioxide and acidity, the sodium thiosulfate decomposes rapidly, right? So bacteria and acid decomposes sodium thiosulfate rapidly. So sodium thiosulfate is not a primary standard. It has to be standardized using a dichromate. So that's why this titration is carried out in two steps. The first step is to standardize the supplied sodium thiosulfate solution, and then you will use that standardized sodium thiosulfate to titrate copper. So let us first of all consider the standardization of the sodium thiosulfate solution. What we do, again, using a pipette, we first of all pipette out 25 milliliter of the dichromate solution in a conical flask. And to this solution, we add 6 milliliter of concentrated HCl and 10 milliliter of 10% Ki solution. So 25 milliliter of dichromate is pipetted out in a conical flask. You add 6 milliliter of concentrated HCl and 10 milliliter of 10% Ki solution. And what will be the reaction? Dichromate will react with iodide. Dichromate is an oxidizing agent. Iodide is a reducing agent. So dichromate will react with iodide, and this iodine will be produced, right? And this iodine will be titrated using sodium thiosulfate. And knowing the amount of thiosulfate consumed and knowing the volume of dichromate that was taken and the strength of dichromate from V1S1 equal to V2S2, you can find out what is the strength of the sodium thiosulfate solution. So first step is that you add to this solution 10% Ki, and I have told you that Ki in presence of sunlight can give iodine. So in order to complete the reaction, what you do, you close the mouth of the conical flask using a small watch glass, right? And then keep it in dark for 5 minutes so that the reaction between dichromate and iodide is complete. And in the meantime, you prepare your burette by having the sodium thiosulfate solution. So after 5 minutes, when the reaction is complete, you take out the conical flask, and to the conical flask, you add 150 milliliter of water. Why? Because initially we have added 6 milliliter of concentrated HCl. In presence of strong HCl, you know sodium thiosulfate will react, and this kind of decomposition may occur. Sodium thiosulfate plus proton gives you sulfur plus sulfur dioxide plus sodium ion. So sodium thiosulfate decomposes in strong acidic medium, depositing sulfur. So to decrease the acidity of the solution, you first of all dilute the solution using 150 milliliter of water, and then you start titrating it with sodium thiosulfate. Now note, though we shall be using starch as an indicator, but we are not using starch from the beginning. So we have a concentrated iodine that is liberated. First of all, we start the titration with sodium thiosulfate, and the black brown color of the solution will gradually fade because iodine is being consumed. And as the solution the iodine concentration becomes lower, when you get a straw yellow color, as we shall see during the video, when the solution becomes straw yellow, at that point you add the starch. So starch addition will give you blue color. Then complete the titration using addition of sodium thiosulfate. When the blue color completely vanishes and you get a colorless or light green color, you should get a light green color because dichromate has been converted to chromium 3 and chromium 3 has green color. So really the solution background will be light green. So a light green color will indicate endpoint. So I repeat what you are doing. You prepared out 25 milliliter of dichromate solution. You add 6 milliliter of concentrated HCl and 10 milliliter of 10% Ki. You put the whole solution in a dark, right? After covering the mouth of the conical with a watch glass, allow it to stand for 5 minutes in the dark, and in the meantime you get your burette loaded with sodium thiosulfate. Then after 5 minutes you add 150 milliliter of distilled water and start titration using sodium thiosulfate. The initially deep brown color or black brown color of the solution will gradually fade, and when the solution becomes sufficiently weak in color, the straw yellow in color, then you add starch, the solution becomes deep blue, and then complete the titration until the blue color vanishes and you get a light green color endpoint, right? Now, if you keep the solution for some time, the blue color will come back. Why? Because there is excess potassium iodide in the solution. So excess potassium iodide will react with oxygen and sunlight, and iodine will be produced, and that iodine will give back the blue color. So to remember, the first endpoint when you get blue to colorless or light green color, that is your endpoint. But if you keep your conical for some time on the desk, the blue color keeps coming back because there is excess potassium iodide in the system, and that reacts with aerial oxygen in presence of light, and iodine is produced. Second question about this experiment is that why we are not adding from the iodine, why we are not adding starch from the beginning, why we are adding starch after sufficient amount of iodine is titrated and it has the solution color has been converted from deep brown to straw yellow. The reason is that if when iodine reacts with starch, if the iodine concentration is low, then iodine starch adduct is a weak adduct, and all the iodine that is adhered to, that is added to the starch can be taken apart by titration, can be taken back by the titration. So in low iodine concentration, starch iodine adduct is relatively weak, and it can be dissociated during titration, and all the iodine can be titrated. On the other hand, if you add starch when iodine concentration was quite high, just like the beginning of the titration, then what happens? Some iodine molecules forms very strong complex with starch. Starch and iodine, that binding becomes very strong. At least some of the iodines will form very strong bonding with the iodine, it will trap in the iodine, a starch complex, and that iodine cannot be taken out during titration. So that's why we are taking the precaution that during the titration, we do not add starch from the beginning of the titration. You first of all start the titration using thiosulfate, and then when the iodine concentration decreases and you have a relatively lower concentration of iodine, then you add starch and you get the blue color, and you can easily titrate it to get the full iodine. So this is the standardization of thiosulfate. And before going to the iron titration, I will show you the video for the standardization of the thiosulfate.
Of copper, we first take sodium thiosulfate
So this
solution
is colorless thiosulfate solution.
and fill up the burette up to 0 mark, and it feed into the burette stand. First we pipette out N by 20 K2C acquisition 07, that means potassium dichromate solution, into the conical flask. Then we take hydrochloric acid 6 ml and add this 6 ml hydrochloric acid into the potassium dichromate solution. This is 10% Ki solution. We take 10 ml of 10% Ki solution and add this Ki solution 10 ml into the K2 PCF207 solution. Look at that. The
So you
color
get a
is
deep brown
deep,
color. You look at
and
that.
it is now brown color. As the iodine liberated, so we covered the solution with a white glass and then placed into the lower disk, that means inside the dark disk. We have to wait for iodine liberation. Out the solution from the dark space now.
After 5 minutes.
Then add into it 150 ml distilled water. Look at that. This is 100 ml and this one is 50 ml. So total 150 ml distilled water add into the solution. Now start the titration quickly with sodium thiazide. Look at that, the color is now straw yellow. In this straw yellow color,
You see,
light yellow color.
deep brown color has vanished and now the color is much lighter.
This is straw yellow color. Now we stop the thiazide addition. Then we add into it starch indicator. Again we start the titration with sodium thiazide.
So you see the
This is the endpoint color.
very light green color due to
So
chromium
blue color
3
is completely vanished and we get the endpoint color. This is the endpoint color of titration and we take the urate reading.
So you see, some students get confused that here the burette reading is the total burette reading. That is before addition of starch, you take total summation of the reading before addition of starch and after addition of starch. It is not that you take the burette reading after addition of starch. You take the total burette reading starting from the beginning of the titration up to the point where the blue color of the starch vanishes and you get the end point. So that is your thiosulfate standardization. Okay. Next we go to the copper part. Now again the principle of the copper titration is that copper, you have cupric ion. Cupric ion reacts with iodide. Cupric ion is reduced to Q plus. 2 cupric ion is reduced to 2 Q plus ion, 2 electron, and these 2 electrons are picked up by iodide and it is converted to iodine, right? So overall reaction is 2 cupric ion, right, plus 4 iodide, giving you iodine plus CO2I2. Okay, so that means 2 iodide ions are simply used as a anion for complexation of the Q plus ion, and 2 iodide ion undergoes redox reaction. They are oxidized to iodine. Okay, so here cupric ion is reduced to Q plus and iodide is oxidized to iodine, and this we shall estimate. The liberated iodine is titrated using sodium thiosulfate, and from there we can know how much cupric ion is present. So what is the procedure? Again, the procedure is you prepare out 25 milliliter of the supplied copper solution in a conical flask. Then here the pH control is very important during this reaction. So initially cupric or brass was dissolved in strong acid medium. So you have to keep during this titration, you have to keep it in a weak acidic medium. So what you are doing, you are first of all adding drop by drop ammonia to the solution with continuous shaking. So when you add ammonia to the solution with shaking, you will find that the acid will be neutralized and a light blue-green color of basic cupric hydroxide will be precipitated. Right? This cupric hydroxide will be precipitated. Remember, if you add excess ammonia, then this precipitate will dissolve. Right, this precipitate will dissolve and it will form a cupramine complex. Then then you have to do certain additional precautions. So try to avoid adding excess ammonia. Then add uh, your acetic acid, right? Small drop bite of acetic acid till the precipitate completely dissolves, and then add 2 to 3 milliliter acetic acid in excess, so that you have cupric ion in weak acidic medium, cupric ion and acetic acid. Then to this solution add, like before, 10 milliliter of 10% Ki. So, and keep it in dark for 5 minutes. So cupric will be reduced to cuprous, iodide will be oxidized to iodine. Now we shall titrate. We shall titrate iodide. This liberated iodine using thiosulfate. So we go on adding like before, thiosulfate initially. The deep brown color goes to light yellow. At this point we add starch. Again blue color comes. We go on titrating sodium thiosulfate like before. But here there is additional one point. Additional point is that when you go on titrating with sodium thiosulfate, then see carefully the color change. When the blue color nearly vanishes, then to the solution you add 1 gram of ammonium thiocyanate or potassium thiocyanate. So there is this additional step. You add 1 gram of ammonium thiocyanate or potassium thiocyanate to the solution when the blue color is nearly vanishing, and then shake the solution well. You will find the blue color intensifies. I will explain why this step is required. So blue color will intensify. Now complete the titration with thiosulfate when all the blue color vanishes, and since in the background you have cuprous iodide or cuprous thiocyanate which has got cardi white color, so background will be cardi white. Now the question is, why in this titration we need additional precaution, and before the blue color completely vanishes we are adding ammonium thiocyanate or potassium thiocyanate? The reason is that at this point when we have added cupric to the cupric ion solution Ki, Cu2I2 was formed. Now experimentally it is found that when Cu2I2 lattice is formed, this is an insoluble precipitate, right? When Cu2I2 insoluble lattice is being formed, solid lattice is being formed, then this insoluble Cu2I2 lattice trap considerable amount of iodine inside it. So quite a considerable amount of iodine that is liberated during the titration, then during this reaction, is not available for titration. It has been trapped inside the solid lattice of cuprous iodide, and unless and until you take some precaution, that iodine will remain untitrated. So to take out that trapped iodine, what we are doing during the almost near the end point of the titration, we are adding thiocyanate to the solution, either ammonium thiocyanate or potassium thiocyanate. What it will do, that cuprous iodide will react with thiocyanate and it will form cuprous thiocyanate. Why? Because compared to cuprous iodide, cuprous thiocyanate is more insoluble. So when you react insoluble cuprous iodide with a potassium thiocyanate solution or ammonium thiocyanate solution, there will be breaking of the cuprous iodide lattice and there will be formation of the cuprous thiocyanate precipitate. Now you are breaking the cuprous iodide lattice, and when you break the cuprous iodide lattice, then the trapped iodine will come back to the solution and it is available for titration. That's why at this point, when you add ammonium thiocyanate, when the blue color nearly vanishes, Then after addition of thiocyanate, if you start the solution, if you shake the solution, you will find the solution again becomes blue in color, and that is because the trapped iodine has been liberated, and the trapped iodine gives you back the blue color. So you have to complete the titration when the trapped iodine has been liberated and all iodine is titrated, and you get the Q plus iodide. So let us see the video for the copper titration.
Now estimation of copper, we have to first take the copper sulfate solution 25 ml by pipette and take it in a conical flask. Now we add 8 drops of liquid ammonia with setting in the small amount of precipitate is added. After that, the precipitate is appear, so we stop the ammonia addition. We have to take the glacial acetic acid and add it into the ammoniacal copper sulfate solution till the precipitate completely disappear. Look at that, the precipitate completely disappear, so we stop the acetic acid addition. This is Ki solution, 10%. We take 10 ml, 10% Ki solution in measuring cylinder and add it into the main solution. After addition of 10 ml 10% Ki solution, that iodine is liberated, we cover it by a watch glass and place inside the disk. That means in dark place for 5 minutes. Now we take it out the solution from the dark place and add into it 100 ml distillate. Now we have to start the titration, titrate this solution with standard sodium thiosulfate. Look at that, the straw yellow color is arise. Then we stop the thiosulfate addition, add into it 1 ml starch solution. Now we add into it 1 ml starch solution and repeat the titration. After addition of starch, we again add sodium thiosulfate. When the solution is light blue, this color, we stop sodium thiosulfate addition, add into it 1 gram ammonium thiocyanate. Mix it and titrate. This is the endpoint color, which is milky white. Repeat the fast titration, that means.
Okay. So you take the results. So dichromate preparation is like before. So I have given you already the data for dichromate preparation. Now the standardization of thiosulfate. Here the volume of thiosulfate is 23.8. Write down the volume of thiosulfate. Initial volume 0 and final volume is 23.8. 23.6 and 23.8. 23.8, 23.6 and 23.8. take the mean volume, it will come around 23.8. So you can take two concurrent readings, 23.8, and find out the S2 using V1S1, V2S2 formula as given here. And then the copper, for the copper titration, you take the readings, volume of thiosulfate required. Here, obviously, volume of copper taken is 25 milliliter, and volume of thiosulfate required is, write down, 9.0, 9.0, and 9.1. 9.0, 9.0, and 9.1. And from this, you calculate the amount of cubic ion using the formulae which are given here. I shall set the assignment in the classroom, and you submit your practical. You submit preferably in practical notebooks like that. So you write the theory, you write the experiment, right, and then you submit the results in the tabular form. So you do that way. So you have to write the theory, some amount of theory. You have to write the procedure, and you have to write the experiments also. And also, please give the heading of the experiment, and clearly write your name, roll number, etc., etc. So, any question? So videos has been uploaded. The instruction is also uploaded in the classroom. I will only set up the assignment for this ferric and cubic titrations. Okay. Any question? Okay. Okay. So I'll stop here, right? And I will meet you in the next Monday.
Thank you, sir. Thank you so much.
Yes, this is the lab class. These are the two experiments which I am supposed to show to you. So if you have any question, you can later ask me or WhatsApp me, etc. Right? Okay. Thank you. Thank you.